Anyway, this is the same lesson we are going on again. The base 4 we sang here, 4, okay, floating floating point numbers is 2 instead. Is it's just we can say 2, right? Is 2 instead, right? Instead of 10. Yes. And because of that, anyway, of that, numbers that are numbers numbers that numbers that are exactly 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 powers of 2, yeah, simplest are the simplest to represent. Yes, this is the short way to represent numbers, right? We don't need to write all of these zeros and things. So we can represent with the binary system like that. So the computer will be very fast to do it, and computer can represent irrational number, and also, yeah, also, I mean, the fractions and the other ones, the floating numbers, and more, okay? Let's say here, what we can say, let's take this information, no, this, just this one here, let's duplicate it and come here. We need now, I don't want to go really for lots of time again for this. Let's come here and say 128, and for 128, let's do, this is 3 time, no, this is not 3 times, sorry, this is 1 time, right? You know that 1 time is 7 power of 2. Normally we know it's already 7 power of 2. So and this one is, we have to take this one, let's take it up here, maybe, no, it's a little crazy stake there. Okay, let's do it 7. Okay, we know what is it, right? Already 128, just we are going to multiply with 1 again for explain situation. And let's do other one here. Let's come again here, and 256. Okay, let's do it. It's one time, it's what, one time, it's 2, so 8 power of 2, right? Let's do 8 power of 2. Yes, the computer doing same thing, like decimal system, we're saying 5 power of 10s and something like that. So we're saying ones, I mean, about points, uh, uh, about positions, we're saying 1 power of 10s, it's 10s, so it's ones, and 0 power of 10s is ones, and 1 power of 10s is 10s, and 2 power of 10s is 100, and it's going all the way like that, right? In the computer we're saying same thing, we're doing same thing, is saying one time this thing and doing something like that. Anyway, you got it, right? So let's go other point here. Now we will write something here again. I will say, let's come down and we can say numbers. No, right. Numbers. Why? Between numbers between powers of powers of two look like this is the important place. I'm so happy to show you here. Yes, this place is important, crazy important. Let's come and say 160. Let's do it. You can't do it with the 7 power of 2 or 8 power of 2 or 5 power of 2, or really you can count what you need. You can try. You can try it really. Let's do it. 1.25. We're doing like that. Time multiplied 7 power of 2. What do you think? It's crazy. I know what's happening there. Let's take it. Yes, just come here. Okay, 160 is just like that. 1.25. Okay, also you can think like minus 2, so minus 2 power of 2, right? Like that, I think, right? 1 divided 4, it's right, like that. Anyway, now what I want to do here, I will show you the map of this way, the path of way. The 160, this one is that, and 192, it's equals, let's think about that, but don't think, okay, for now, and say there's 150, 150 time 2 power of 10, I think. No, not 2 power of 10, it's 8, I think. What do you think? This is 8, right? This one is 8. Let's put there and say 8. This one is that. Maybe I can take down, but anyway, you know what I'm doing here. And this one. Look at, we are not working with 260, 156 like that, or 128. No, we are looking with different of things, okay? We have to represent different. So we have to understand concept of, okay, so how the computer doing these jobs, this works, how computer doing, really it's amazing. So now this one is 1.75, and plus it's 2. Let's duplicate it and come down. This one is 7 also. Let's do it 7. Yes. So it's mean 128 times 1.75. It gives us 224. Okay, let's. I think we got it. What is turning here? No, don't do it. Let's come down. We're going on again. Now we will say, what about non-integers? What about non-integers? Let's speak about that. Once again, powers of 2 are the simplest to represent. Really, it's not too much difficult. I told you 0 power of 2, 1 power of 2, 2 power of 2, but if you represent 187, how we can do that? Okay, you have to use some numbers like that, 1.73 times 2, so 7 power of 2, something like this, crazy. Anyway, let's come down and say 0.50. Let's represent it. How we can do it? This is really not too much difficult. You know, you have to divide 1, divide 2. How we can do that? So it will be like 1 time minus 1 power of 2. Yes. So minus 1 power of 2. Because it will be 1 divided 2. And what will be? It's 1 divided 2. It will give us again 1 divided 2. It will just divide 1 like apple. Just think like apple, okay? It will divide 2. Okay, this is the 0.50, 0.5. And let's look at for the 0.25. 0.25, it's the same, just we are doing minus 2, right? Minus 2, it will be 2 times minus 2, it will be 4. Minus 4, it's 1. Then we are doing absolute numbers, we are taking absolute numbers. It's 1 divided 4, it will be 0.25. And just do it with me. Let's say 1 time 2, and just take this one and duplicate it and come down and just put here with minus 2. It's all the information is that. Okay, this one is amazing. Now we can do really just, I told you 1 divided 4, it's already 0.25. 1 times 0.25, it's already 0.25. We can represent 0.25 like that. We can represent 0.50 like 1 time minus 1 power of 2, like that. Let's come down to another one's floating point. Floating point can also represent fractions between powers of 2, fractions between power of 2. It's fractions and power of 2. Really, we can do it also. Yes, how we can do that? What do you think? Let's do it. All the time we use different knowledge of, so about that. Let's do it. We can say 0. Let's take 1. 0.750. Now what do you think? Between power of 2. We have to do some crazy things now. How we can represent it? Let's say this one is 1.5 times minus 1 power of 2. Minus 1 power of 2. Okay, let's come here and take this one. It's power of 2. Yes, this one here. Maybe take a little bit down. Well, anyway, I will not touch there because I have to show the other one. I have to be fast. 0.375. It will be. This will be. What will be it? 1.5 again. 1.5 times 2, and it will be minus 2 power of 2. It will be. I know, 2 times 2. It will be 4. Minus 4. It will be. I mean, about radicals. It's have to be like absolute. It's not have to be minus. Anyway, it will come out from radicals. So also exponentiation. Maybe you know all the information about it. So it will be 4 and 1 divided 4. So it will be 0.25, something like that. Then 1.5 times 0.25, it will give you 0.375, something like this. Crazy numbers. Okay, we know now how computers really works like that. How computers really knowing these floating numbers, or there is some rules. The computer saying us, I'm doing this all of these jobs like that. Okay, let's come down, and the last thing we have to add here. Once the computer determines, once the compute once no what I'm doing, I tagged screenshot, sorry. One the computer the computer determines the floating point representation, the floating point representation, representation for a number, for a number, for a number, just come down, for a number, yeah, for a number, it stores that in bits. It stores that in bits. Modern computers use a modern, yes, well, let's do it right. Why? Yes, modern. I will be crazy here. Oh, modern computer. I don't want to use again this word. Modern computer use a 64-bit system that uses bit system that uses 1 bit for the sign, bit 1 bit for the sign, yeah, 1 bit for the sign. Where is it? Right, for the sign, and 11 bits for 11 bits for the 11 bits for the exponent. Yep. And 52 bits for the number in front, for the number in front. Okay. Here's 0.5, this number. In that binary floating, floating, binary floating point representation. What do you think? Like what? Representation. It's like 00. 1 all the way 0. Yes. Yeah, it have to be 63 1 for sine. The 11, this one I think here for the exponentation. I mean, I think exponent, and the other ones is all the way like that. So I mean exponent. It's I showed you this one. This one is the 11 numbers representation is like that. The other one is just zero, so nothing there. But this is crazy, really. If you count it, it will be crazy numbers there. So I'm saying here the exact translation to bits, translations to bits, sent to bits is more complicated, complicated, more complicated than we can go into. Then we can go into here. Let's come down here. But is a great topic. But is a great topic. Topic. I mean, it's a great topic for those of you. For those of you who want to dive deeper, who want to dive deeper. Yeah, deeper, or you can think like that. Anyway, this is the crazy point, but you can go really 0.0 power of 2, 1 power of 2, 2 power of 2, 3 power of 2, all the way like that. Just please go. So, anyway, the last point. Now we will speak here about what we will speak about. Let's take this information from here and come down and just really come here and do it, and really just we will delete it and we'll say round of errors. Okay, this is the other topic. Now we will learn something also here, and through with this experiment we will go to practice questions, and we will finish it. We will come end of this course, end of this way. So we will go other topics later. Now we will write lots of again floating point representation. Floating. Let's do black. Where is it? Let's say black. Floating point representation still can't fully represent, still can't fully can't fully represent all numbers. What is this? Not can't. Oh, fully, not fully represent, or not represent. It's represent, represent all numbers. Yes. However, consider consider our consider is not consider fraction the fraction 1 divided 3 dividing 3 and its floating point representation, and floating floating point, and it's really floating point representation point represent. Oh, please stop. Not real representation. Yes. Now I will show you with example it. Let's come here. I will say 1 divided 3 equals, we know that. But here, so it will go all the way. So if you divide it 1 divided 3, really there is no limit to stop this number because it is like p number. Anyway, I will show it you. 1.3 times minus 2 power of 2, it will be 1 divided 4. So we can say 1 divided 4 times 1.3. If you multiplied it, then you will see what I'm saying here, right? So really you will understand what I'm saying there, because it is important point to understand concept of this verbs or technology. I mean, let's come here and say it's minus 1. Let's put this minus 1 above 2 exponent. I mean, so let's also, I need one line. Where is the line? Line is just thank you. There is no place to say this numbers all the time going. So what I am saying here, I mean, this one is here. Let's come a little bit right. Oh, why? Let's think this one is here. I think right. So it is just thank you. It's going all the way like that, right? If you divide 1 divided 3, it will give us some numbers all the time going like that. But we are just humans. We are just doing 1.3. It's all. Anyway, and we're saying in binary, I will do bigger, come down. In binary, and in binary, let's say, let's tag this. How I can tag this one. Just tag this one again. Tag down here about 3. Yes, in binary 3, but this is still on on infinitely repeating sequence. Yes, we know that, right? For that we know also p number, there is no limit, so repeating all the time infinitely. So I mean 1 0 1 0 1 0 1, and how many 0 1 0 1 0 1 0 1 0 1 and 0 1, and all the time going like that, right? I mean, we're speaking about 3 point of the plays. Yes. Now what I want to write here, I will write now. Now we will write lots of things in this point. I will say, let's put one space too much in this place. Where I'm going, no, come back to this place and go up and tag a little bit, right? Yes, let's start to write. Now we will write lots of things, but don't worry about that. Okay, this is the good information for the future. It will help you. It will help you to reach some situation, some position for your life. We can't store an infinite sequence. We can't store infinite sequence in a computer. In a computer, right? Yes. At some point, the computer has to end the number The computer has to end the number to end has to end the number somehow. So somehow either by copying either by copying. Still I don't know this word to explain you. I think this one is not copying, it's copying like that. I don't know what is it. It of or rounding. Rounding. Yes. Rounding to the rounding to the nearest nearest floating floating point number. Yes, we know that. Computers have to do that fairly. Computers, computers have to do that fairly. Yep, fairly often, as as even fractions, as even fractions like like leakage prone. By 10, which is a start, which is a short, I mean short, which is a short 0. 0.1, 0.1 in decimal. So right, we know that in decimal. In decimal, end up as end up as infinitely. Let's come down. Repeating sequence infinitely repeating sequences once converted to to once converted to binary to binary. Yes, converted to binary. It's the good information, I think. We often we often we often don't notice don't notice the lower precision of the numbers, the lower precision of the numbers, yes, of the numbers representation until representation until we use it in calculations, right? Yes, that's when we can experience that's when we can experience a round of error, I can write round of error. uh, so this one I will tag in the place. I can tag this one as can be read. Okay, let's come down. round of error and do something like that and take back black kind of things. And okay, let's say in the results, in the results, just like this one, in the results. Okay, just tag, not too much about that. Okay, and the last information here I will add. Yes, my friend, now we will go on again from here, and I will say now here, here's a program, yes, that attempts to add, right, 0.1 plus 0.1 plus 0.1. So in the in the non-computer non-computer world, we know that we know we know that's we know that's 0.3, but but in the computer in the computer yes, each of the 0.1 each of the 0.1 values is stored is a of rounded of binary binary fraction fraction and then and then they are added together together they don't they don't quite is it not don't like that don't quite no it's like that it's quite equal equal what we expect. So this is really important, really, if you are anyway, I will give you lots of information again for it. So okay, what I want to show you now, let's open again Visual Studio Code there, and I want to show you something here with experiments 2. Maybe it will be good information for yourself. Let's come here. So let's do this place is good, right? Just say var. Also, we have lots of variable representation mode. We can say var. Also, we have some kind of if I remember which one is I don't remember. So normally I'm Python programmer. I'm not a JavaScript programmer, but uh, just I don't remember good now for now. Okay. Anyway, later I will share with you all my experiments about that. Anyway, we're saying var results. We can result. We can say 0.1, 0.1, 0.1. So we know 0.1, 0.1, 0.1, and say console.log and just put result there. Okay, let's save it. Let's go live. Okay, if I remember also this, really uh, I will share with you this information. Just go inspect. In the console, let's look. This one here. Anyway, I can delete the other one. Let's take them in the, no, just this ones. Let's take them in the comment. Right. Just do like that. Yes. Yeah, now you will see 0.30000 all the time like that, and 4 staying that. I'm in that, okay? The same information I'm in. So our expect is not that, but so it's not same, okay? It's not equal that. But in the normal world, so in the normal non-computer world, we are just accepting it like 0.3, okay? But in the computer, if we are working on precision, uh, if you are working on precision jobs, I mean precision works, like if you are doing some physics research or physics implementing, we are implementing some things there. Just we have to really count all the details in this place. We have to think too much good. Anyway, you saw what I did here, and I will delete this part of place, and I will delete also here. Okay, I come back to here. Maybe if you want, I can write here this information, but okay, I think you got it, right? So it will be something like that. It will be var result. Yeah, yeah. Also, I want to add here information. I mean, I can show it you VS Code. In VS Code, we have also let variable. It's just give you some permission to work on it, right? So we have let. So yes, this one. You can do also with let. This one. And really, if you want, sometime you can change this variable result 1 equals result, and you can say result. You can export your other variable here, and just if you say like that, then just think you want to log result 1 1. Anyway, you can say result and plus 1, something like that. What do you think, what will happen here? Say go live, what will be here? We will look together. Yep, just say inspect. Oh no, it's not that. But anyway, it's just you can see also our codes. I told you this later. We will speak about programming. Let's come and say inspect. Just we need to inspect. Just I want to show you this thing also. Maybe the console. Yeah, 1.3. Have you see? This is our information there. So just I will export our variable into other variable. This is the variable exporting. Anyway, just I will do it also like that, and We just will close VS Code and we'll close to here. I will come here and I will say result equals 0 0.1, 0 0.1, 0 0.1. And if you say println also console.log, it's really, I don't know this println too much is different. In Python we're using print, but in this different. So uh, println, I told you console.log, you can't think too much about it. Let's say this is our inputs, as our inputs, no, inputs, inputs, yes. This one, the outputs. So already I showed you 0 point all the way. It's going like that and 4. So you can think like that, okay? Is that. And the more bits we can use, come down here. Yeah, maybe here. Yes, let's come down. Yep. Let's little go this place. Yes. The more bits we can use, the more precise, the more precise, the more, the more, more precise our numbers. Our numbers. It's all about bits, really. If we expanded our bits range of bits, then really we can represent all this. I mean, the important place about precise, okay? Because this is the important point I told you. Precision is too much important if you are working on rocket technology or cars or some important things, then really you need. So our numbers and calculations, calculations will be in modern 64 bit system systems offer a high enough precision, a high enough precision for low stakes. Yeah, really, this is also important place. Calculations. Yeah, if you are really, if you are expanded, expanded a range of bits like 64, if in the future happen like 500 bits or 1000 bits or something like that, then your own precision will be very good than other ones, the other one, so less one, because the important place computer can represent this situation. So I mean, normally if the in 64-bit system, just think your like 1 divided 3, it's all the time going 0 0.3, and it's going 0 0 0 0 0 0, and uh, the large of integers, we know safe of integers, it will stop in the one place. It's 53 power of 2, then it will stop there. But just think, if you make it like 1000 bits, 2000 bits system, then it will go all the way like that. Then our precision will come good because numbers want to go lots of way. So just we don't have store maybe to store these numbers there to make some calculations. Anyway, calculations, let's come down and perhaps at some point in your life, at some point in your life, point some in your life, you'll find yourself, you'll find yourself reading programs, writing programs that calculate, calculate voting outcomes, voting outcomes. Yep, outcomes. Power self-driving car. Power self-driving car. Power a self-driving car. I told you the important point here: self-driving car. Precision too much important there. Just little bit precision problem or overflow problem, round of problem. It will make lots of problem about driving car or about customers or about some person, about passengers, car, or even launch a rocket. Really, this is will be crazy. Just you have to control your own things. Okay, when the stakes are high, high precision matters. Really. Now we have numbers, limits, overflow, and a round of practice questions. What I want to do here in this point, I will write this one here. I will come down really, and this point. Yep, maybe here. Right? I just want to come here. I want to write numbers, limits, numbers, limits, overflow, overflow, and round off, and say practice question, question, questions. Okay, let's take them in blue maybe. Okay, we have some question here. Question one. Okay, let's do black, then black. Let's come here and write Ernesto. Let's light this as here. Yep. Ernesto writes this code. Calculate the final, to calculate the final cost of a meal, cost of cost of a meal with a with tip of 20 percentage, so 20%. So now we have here this information: meal Meal like that. It's like that. It is, you know what is it, right? This important point, floating point representation we have here, right? What do you think? Anyway, I don't want to go detail. The width tip will be again, maybe, and again, this one here, it will be 1.20. Just take this one also far by here, like that. No, just go up. Yeah, do something else like that. Okay. The last one total will be, yes, this one. But it will be meal plus with, no, not plus, sorry, time, because we are looking for percentage with tip. Now we have to multiply this one to this one. So this two, anyway, I will come down. They are surprised to see that. They are, they were surprised. They were surprised to see that total stores, total stores, the volume, the volume like 11.93, and all the time is going like this. Instead of instead of this one. Yeah, lots of information there. You see, what is the best explanation? What is the best explanation? Explanation is the best ex, explanation, right? For that result. For that result. Choose one answer. Come down, we don't have place there. Now we have here, yes, D. Okay, let's write lots of things here. The first one, the arithmetic operations, arithmetic operations on floating point numbers resulted in a in a round of error of error round of error, right? The arithmetic operations on floating point numbers resulted in a round of error. What do you think? There is some K. So normally have to be like 11.64, but the number is like that. The arithmetic operations on floating point numbers resulted in a round of error. This one is true. The other ones I will write here. An integer overflow. An integer overflow. Error. Error occurred. Occurred. This one is really not true because we don't have overflow problem there. So it's all about round of error because we want 11.64. There is number coming lots of this way. I told you about representation. We have some differentiation there. So it's not about overflow, okay? This is not about integer, okay? Anyway, the computer stored the result. The computer result store the computer stored the result the stored the result, right? Yes, the result with floating point representation. With floating point representation representation instead of integer integer representation. Let's look at that. What is it? Saying the computer stored the result in the floating point representation instead of integer representation. What do you think? The computer stored the result with floating point representation instead of integer representation. How the computer can represent it with the integer representation? This is not possible. I told you. Power of 2. We are looking power of 2 with this number. I told you we do a lots of example. Where is that? Maybe come right. We are doing operations, so computers doing operations like that. So we are also doing sometimes we don't want to say thousand like 1000 something like that, or 100,000 100,000.000. We are just saying 3 powers of 10 or 5 powers of 10, and we are showing our numbers. The computer doing same thing. So this is the not good explanation for the result. This one is not true. So this one is not true. Not best one to explain the situation. The other one, the result was too large. The result was too large. Too large. Of a number to be stored. Of a number to be stored. Stored in floating point representation. In floating point representation. Point representation. The result was too large of a number to be stored in floating point representation. Yes, but what we can do, so our explain it, its best one is first one. The arithmetic operations on floating point numbers result in a round of error. There is a point, the key point is round of error, okay? Because the problem here I showed you, we want 11.64 whatever number all the way going like that. So it's not true value, okay? But I told you computer cannot represent everything good. It's all about precision, okay? The problem here about that. So the question 2, let's come here. Question 2. It's okay. We can together. The video sharing site. The video sharing site, you know that? YouTube. YouTube. Originally shared the number. Originally stored. Sorry, not shared. Originally stored number. Stored number. Stored the number. The number of video views in a 32-bit signed integer. Okay. Now, then the viral hit. So Gangnam Style, Gangnam Style, receive it more than more than more than two like that, and 48 183 uh, 6 or 7. These numbers views, yep, views, and more than any other video, at that time, more than any other video at that time. Okay, now and and YouTube YouTube could not display not display an accurate number accurate number of views views until they change it their code. Okay, what is the best explanation of what happened of what happened? Choose one answer here. Again, calm down. Okay, do we have A, we have B, we have C, and we have D? Okay, let's do together here. Now the first one is saying incorrect use of integer instead of floating point representation. What is that? What's saying? Incorrect use of integer instead of floating point representation. This one is saying incorrect use of integer, incorrect, or floating point. I think this one is not true, really. It's not best explanation. It's not about that. Also, the other one is saying integer overflow error. This is really amazing explanation. So overflow error. There is overflow error because why? Our system is 32-bit. I told you 32-bit, right? So let's look at here, the countdown. Saying the video sharing site YouTube originally stored the number of video views in a 32-bit signed integer. Then the viral hit Gangnam Style received more that than this I think 2,147,048 483,647 views. I think there is some overflow error, right? This one is true answer. I will come here and really just what I want to do. I want to select this one as true. Maybe I can go up. There is also the which one is true answer? I think yes, this one is A, correct answer here. This one is, oh no, this one is true. It's okay. Let's come down. The B is true. I told you integer, the overflow error. Okay. Mm, I told you all about overflow. Okay, you know overflow. What is it? 32-bit. This is more than 32-bit, and there is no representation, then it's problem happening. And YouTube, I think, control it later. Some example around of error in floating point floating point represent float point arithmetic. It's not about round of error. I told you it's 32-bit, but there is too much information. It's about overflow. Because I told you, I give you some example with the 8-bit that we told the leftmost. So the one of them, it's about positive, it have to be sign, right? Like we put there plus divide minus, so plus and minus for make operation. Then other 3-bit all about actual values, right? It is like that. 30-bit 32-bit, they're only for integer numbers, but I think the Gangnam styles, I mean this video got too much views there, takes lots of views there, and really these problems happen is, I mean, all about integer overflow error. And we say limited precision of floating point point floating point point numbers. Limited precision of floating point numbers. I think it's not about it exactly. It's about so so it's all about integer overflow error. Okay, that's this one. Okay, let's. I will do something now. The two example is good for it. The last one can be maybe um, it's so important place. Where is my coffee? This is now iced coffee. Really, it's not like normal coffee. Oh, all so the we will look now question 3. Mm, we will do together also this one. Really, there is amazing things. Let's do some Maybe this one. Okay. Now we will do, let's say, question 3. Okay, we have 3 questions for this place. We will say consider computer computer that uses 5 bits 5 bits uses 5 bits, right, to represent positive integers, to represent to represent integers positive integers, and uses all 5 bits that's separated bits to represent the value to represent the value. Oh, consider a computer that uses 5 bits to represent positive integers and uses all 5 bits to represent a value, right? Okay. Which of the following operations would result in integer integer overflow? I will say also not that there may there may be multiple answers to this question to this question. Choose all answers that apply. Okay. Think about again. Anyway, I can do with this. Okay, let's come down. Again, think about question, okay? Consider a computer that uses 5 bits to represent positive integers and uses all 5 bits to represent the value. We have 5 bits, power of 2. What happening yet? So power of 5. So 5 power of 2, it will be like what? It will be, what it will be? It will be, if you count them, it will be 32, right? So yeah, so 32. Now the important place here to understand this concept, it's saying which of the following operations would result in integer overflow. Result in integer overflow. Which of the following operations would result in integer overflow? Well, we have lots of thing. I will show it you now. Yes. We have, okay, we have A, we have B, we have C, we have D, we have E, we have F, not V. Okay. The first one, yeah. The first one is 8, 8, 18 plus 14. The second one is it's 12 times 2. The other one is 15 plus 1. The other one is 8 times 4. Another one is 8 plus 4. Last one is 12 plus 2. So, I mean, let's think about these questions. So, here the point plays. You have to understand the power, 5 powers, power of 2, powers of 2. We know that, right? What do you think? Just think 5 power of 2, it will be 31, right? Because 0 power of 2 will be 1, and just add 1 there. Or you can say 5 power of 2 minus 1, it will be 31, okay, not 32. And just look at that. First one is 18 plus 14. It's 32. Really, there is some overflow. Have you seen this? Let's come here. We are looking for what? Integer overflow. It will be really wrong. Let's look at that. I will say this one. So this one is equals 32, right? This one is more than 31. Okay. Other one, look at that. It's this one. It's 24. It's not more than. So there is. It's 24. 24 is not more than 31. So there is. What do you think? Is there any overflow? I think no. So other one is will be 16. 16 is not more than 31. And right. So other one, look at that. 8 times 4, it will be 32. 32 is greater than 31. Also say this one, 32 is greater. Greater, right? Greater. If I'm not writing wrong, it's greater or greater? I don't remember good. I will look for it. My brain stopped lots of video I did here. Greater, right? Greater, I think. Right, true. It's greater. Anyway, greater than 31. It's greater than 31. This one is just. Have you seen the point? It's just is not 12 is not really greater. No, no screenshot. Greater than 31. It's not. And this one is just 14. This is really poor number. It's not greater than 31. So I will take my pencil. I saw their point. They are looking for what? They are looking for integer overflow. Yes, integer overflow is that here? Yes, because 32 is greater than this number. This one is not really, is 24. There is not overflow, and this is not there is also not overflow. 16, 32 we have here overflow again. This one is really not bigger than this number or greater than this number, and this one is not greater than number. So we have these two answer, correct answer here. They are greater than 31. I mean 5 powers of 2. And really there is overflow problem. It's like our first, no, second questions. 32-bit signed integer. If there is lots of views, it's all about integer overflow error. It is the same like this integer overflow. Okay. Okay, it's too much. It's 3 questions we solved together. Thank you so much for joining me. Now I will go to other topic later. So we will all together. The other topic will be about storing text in binary. I mean storing text in binary. So exactly that. The later of this subject we will speak about converting analog data to binary. It will be our subject. So we have 2 subjects then later of this subject, number limits, overflow, and roundoff. It's already finished now here. We did some practice. We will speak about the next topic. It will be about storing text in binary, and other topic, next topic, then storing text in binary. It will be converting analog data to binary. Then all topics will finish. Also, we will go digital information quiz 2. We will make this quiz, and all the way with this experiments, through this experiments, we will go other topic. Then again, we will do some digital information quiz 3, and also all of later then we will do digital information unit test for all our information. Then we will finish it our journey about digital information. And what we will do, we will go, the internet is the most important topic uh, topic of computer science and programming, then algorithms. All the way we will go with our experiments through with our all skills. Thank you so much. It is all for this lesson. So I told you what we will do, all of them. So see you later for now. Thank you so much for joining me. Really, I was tired too much, but I will. So because just I want to share with the people all my experiments. Maybe you will do some more things. You have some dreams. You just imagine your life in the future. Really, I believe you will lots of things there, and programming is a really good job. So just interest with the physics or with the math, and really take lots of their experiments, then really interest with the programming, and really you can implement all your skills in math or physics on programming, then really you can do lots of amazing things with this technology. Thank you so much. See you later. See you soon. So very soon.